first humans to land on Mars will likely be dead within 2 years. Not from a crash, not from a mechanical failure, from the slow, invisible accumulation of radiation that their bodies absorbed every single day of the trip. And every day they stood on the surface. That's not pessimism. That's what the numbers say. We've been sold a version of Mars colonization that sounds like the plot of an adventure movie. Elon Musk has a date, SpaceX has a rocket, and in the breathless coverage that follows every Starship test flight, we've somehow convinced ourselves that getting humans to Mars is basically a logistics problem, just a matter of when, not whether. But the scientists who actually study what happens to human bodies in deep space, the chemists who've analyzed Martian dirt, the psychologists embedded at research stations in Antarctica trying to simulate what isolation does to a crew, they are not nearly as optimistic. And the gap between what they know and what the headlines say is enormous. This isn't a video about why Mars is impossible. It's a video about why it's genuinely, brutally harder than we're being told, and why that matters. Let's start with the thing that will kill you before you even land. Mars has no global magnetic field. Earth's magnetic field acts like a planetary shield, deflecting the constant bombardment of cosmic rays and solar wind that streams through the solar system. Mars lost its magnetic field billions of years ago when its core cooled and solidified. What's left is an atmosphere so thin it provides almost no protection at all. On Earth's surface, you absorb roughly 0.1 millisieverts of radiation per day. On the Martian surface, that number jumps to 0.67 millisieverts per day, about 6.5 times higher. During the transit through deep space, where there's no planetary body offering any shielding at all, that rate climbs to roughly 1.84 millisieverts per day. Do the math on a 2.5-year round trip, 6 months there, 1 year on the surface, 6 months back, and an astronaut accumulates something in the range of 1,000 millisieverts total. That's a 5% increase in lifetime fatal cancer risk at minimum. Some estimates, accounting for uncertainties in the biological effects of deep space radiation, push that figure closer to 20%. And that assumes nothing goes wrong. In May of 2024, a massive solar particle event hit Mars, the most intense ever recorded on the planet's surface. In a matter of minutes, radiation levels spiked to roughly 8,100 microsieverts per hour. To put that in context, a full-body CT scan delivers about 10,000 microsieverts in one go. A future surface crew caught in the open during an event like that would absorb a potentially lethal dose before they could get back inside. The problem? Solar particle events are notoriously hard to predict. You might get 15 minutes of warning. You might get none. Even on a quiet day, the radiation on Mars isn't just a cancer risk. Galactic cosmic rays, high-energy particles from outside the solar system, have been shown in animal studies to cause changes in brain tissue. Specifically, damage to dendritic spines, the tiny structures neurons use to communicate. Studies using radiation doses comparable to what a Mars crew would receive showed cognitive decline, impaired decision-making, and behavioral changes. The people we'd need to be most alert, most sharp, and most capable of keeping themselves alive are the exact people this radiation would be quietly dismantling. Now let's talk about the ground beneath their feet. When the Curiosity rover landed in Gale Crater in 2012, one of its early discoveries rewrote the script on Martian agriculture. The soil contained perchlorate, a highly reactive salt, at concentrations between 0.5 and 1% by weight. Follow-up data from Perseverance confirmed the pattern. Perchlorate appears to be globally distributed across the Martian surface. No matter where we've sent a lander or rover, we find it. Why does that matter? 2 reasons. First, perchlorate is an endocrine disruptor. It blocks the thyroid gland's ability to absorb iodide, which in turn shuts down the production of thyroid hormones. Thyroid hormones regulate metabolism, body temperature, heart rate, and brain function. Chronic perchlorate exposure doesn't just make you sick. It slowly dismantles your body's ability to regulate itself. At the concentrations found in Martian soil, the health effects would be severe and cumulative. Every dust particle that finds its way inside a habitat, every moment of contact with unprocessed regolith, would be a low-grade toxic exposure event. Second, you cannot grow food in it. Experiments using Martian soil simulant, regolith with perchlorate added at realistic concentrations, found that plants fail to germinate. Not just grow poorly, fail to germinate. The perchlorate blocks growth at the seed level. Any vision of Matt Damon-style potato farming on Mars requires first extracting or neutralizing the perchlorate from every cubic foot of soil you intend to farm. That's a massive chemical engineering challenge that people rarely mention when they talk about Mars being self-sufficient within a decade. You'd need a functioning chemical processing operation running at scale before you could grow a single edible plant in Martian dirt. The soil is poisoned. The sky is radioactive. And you haven't even left Earth yet. The journey to Mars takes 6 to 9 months one way, depending on where the planets align in their orbits. That's not a technical problem we're working on solving. That's orbital mechanics. Unless we develop propulsion technology far beyond anything currently operational, a crew spends the better part of a year in a metal can, cut off from Earth, with communication delays that stretch to 24 minutes one way at maximum distance. You cannot call for help. You cannot get medical advice in real time. You cannot pull over. Research stations in Antarctica have served as some of our best analogs for what this does to people. The Concordia station, operated jointly by France and Italy, sits 1,000 miles from the nearest coastline, at an altitude that leaves crew members oxygen-deprived, in total darkness for months at a time, isolated from the rest of humanity for up to 13 months. What researchers found there was not encouraging. Crews consistently showed cognitive decline, slower reaction times, reduced short-term memory, impaired spatial reasoning. They experienced disrupted sleep, elevated stress hormones, and interpersonal conflict that, in a confined Mars spacecraft, could turn catastrophic. Depression wasn't an outlier, it was standard. And here's the part that makes this more than just a morale problem. A Mars crew cannot be evacuated. There's no emergency return window. Once you're committed to the surface, you stay there for at least 14 months until the next planetary alignment allows a return trajectory. If someone breaks down psychologically, if someone becomes violent, if a key crew member becomes incapacitated, there is no extraction. The mission either continues or it ends in tragedy, and the nearest backup is 140 million miles away. If you're still breathing, here's what the planet itself will try to do to you the moment you step outside. Mars has an atmospheric pressure of about 0.087 pounds per square inch. Earth's is 14.7 pounds per square inch. That's less than 1% of what your lungs are used to. Exposed to the Martian atmosphere without a suit, the moisture on your eyes and tongue would begin to boil off in seconds. Blood gases would follow. You'd be unconscious in under 2 minutes and dead shortly after. The suits required to keep a human alive on the surface aren't just backpacks. They're full life support systems that must maintain internal pressure, regulate temperature across a range that swings from minus 220 degrees Fahrenheit in the polar night to a relatively balmy 70 degrees Fahrenheit in the afternoon near the equator, scrub carbon dioxide, and manage the constant threat of micrometeorite puncture. Every extravehicular activity is a high-stakes mechanical operation. A single failure in any component, a seal, a valve, a regulator, ends immediately and irreversibly. Dust storms on Mars don't operate the way they do on Earth. They can grow from regional events to planet-encircling systems in a matter of weeks, and when they do, they can last months. NASA's Opportunity rover, a machine that had been operating on the surface for 14 years, was killed by the 2018 global dust storm. The storm reached a tau of 10.8, compared to a normal tau of 0.5 at Opportunity's location. That means the atmosphere became roughly 20 times more opaque than normal. Solar panels couldn't generate power. Batteries ran down. The rover went silent in June of 2018 and never woke up again. For a human colony that depends on solar power, and virtually every proposed Mars-based design includes heavy reliance on solar, A global dust storm isn't a weather event to endure. It's a survival crisis. You can store power, but storing enough power to run a full habitat through a months-long blackout requires battery infrastructure that would weigh hundreds of tons. And that's weight that has to get to Mars somehow, at a cost per kilogram that is almost incomprehensible. Then there's what happens to your body over time. 6 months of near-zero gravity during transit means the mission hasn't even started, and the crew is already falling apart physically. In microgravity, the human body loses bone density at a rate of 1 to 2% per month. Skeletal muscle mass drops by up to 20% in just 30 days without aggressive countermeasures. Exercises can slow the process, but not stop it. When that crew lands on Mars, already weakened, already skeletal, they step into a gravity environment that's 38% of Earth's. That's stronger than 0G, yes, but research now suggests it's not strong enough to halt the degradation. Studies indicate a threshold of roughly 0.67 G is needed to prevent significant muscle and bone atrophy over extended periods. Mars gravity sits at 0.38 G, below the threshold. And then there's something called spaceflight-associated neuroocular syndrome. SANS for short. In microgravity, body fluids shift upward toward the head, raising intracranial pressure. That pressure pushes against the back of the eyes, flattening the eyeball and causing a form of farsightedness that, in some astronauts, becomes permanent. On the ISS, roughly 70% of astronauts on long-duration missions show some degree of visual impairment. In some cases, it never fully reverses. Imagine arriving on Mars after a 6-month transit already radiation-dosed, already bone-depleted, and potentially unable to read the instruments clearly. Now let's talk about the timeline and the money. In September 2024, SpaceX announced plans to send the first uncrewed Starship missions to Mars in 2026. Then in February 2026, Elon Musk pushed that back again, this time by 5 to 7 years, to focus on lunar missions. This is a pattern. Musk initially said humans would land on Mars in 2024, then it was 2026, then 2029. The average delay on major SpaceX predictions historically runs about 2 years, but Mars is proving to be in a different category entirely. A 2024 feasibility study published in Nature concluded that Starship as currently designed has a fundamental delta-V deficit that makes a crewed return mission physically unworkable without major redesign. As for cost, Musk has claimed the price per ticket to Mars could eventually drop to $100,000. Right now, getting a single kilogram of payload to Mars costs somewhere between $150,000 and $350,000, depending on the mission architecture. A crewed Mars mission, with the life support, food, water recycling, medical equipment, power generation, habitat infrastructure, EVA suits, and emergency contingency systems required, would likely cost somewhere north of $500 billion in realistic near-term projections. That's not a number that kills the dream. It's a number that demands honesty about how long this will actually take. The honest answer? Most space scientists think a crewed Mars mission before 2040 is unlikely. A permanent, self-sustaining colony before 2100 would be an extraordinary achievement. Not impossible. Extraordinary. None of this is an argument for giving up. The science of space medicine is advancing. Radiation shielding materials are getting better. Psychologists are developing better crew selection protocols. Engineers are designing habitats that could be built underground, where meters of rock provide natural radiation protection. Biologists are figuring out how to biologically remediate perchlorate-contaminated soil. Nuclear power systems could replace solar where dust storms make it unreliable. Every problem has a potential solution. The roadmap is real. But the roadmap is also long, expensive, and littered with challenges that the public pitch for Mars colonization tends to skip over. The version of Mars you see in announcement presentations, the gleaming domes, the thriving greenhouses, the happy colonists, is a destination, not a plan. Between here and there lies radiation your body absorbs with every breath of recycled air, soil that poisons the crops you need to survive, a transit that tears apart your mind and skeleton before you even arrive, an atmosphere that would kill you in seconds, storms that could last months, and a price tag that no single company or country has come close to raising. The people who are most excited about Mars, the engineers, the mission planners, the scientists who've devoted their careers to it, they know all of this. They're not hiding it. But the version that reaches you through press releases and Twitter posts and breathless news segments tends to cut these parts out. And when we don't hear them, we don't fund the hard research that would actually solve them. We applaud the dream and skip the work. Mars is worth going to. The science alone would revolutionize our understanding of planetary formation, the potential for life beyond Earth, and the resilience of our own species. But the humans who go there deserve a plan that accounts for the radiation, the poison soil, the psychological breakdown, the physical deterioration, and the brutal physics of a planet that does not want to keep us alive. They deserve the honest version of the story. So here's the question I'll leave you with, because it keeps coming up in the research, and nobody has a clean answer. If we somehow solved every engineering problem, every medical problem, every logistical problem, and we could send a crew to Mars tomorrow, would you go? Knowing the radiation risk, knowing you might never fully come back, knowing the dust, the soil, the isolation, the physical cost. Drop your answer in the comments because that question tells you something important about how we actually value this mission. If this gave you a new way of seeing the Mars conversation, hit that like button. It genuinely helps this channel reach more people who should be thinking about this stuff. Share it with someone who just watched a Starship launch and thought we were basically there already. Subscribe if you want to keep going deep on these topics, because the next video gets into something that'll change how you think about whether we should be looking at Mars at all, or whether there's somewhere much closer that we've been ignoring this whole time.